You can see that there is a 500-gram block that is attached to a spring. It's been given an initial push to the left. We don't know the speed though, and we know that it takes 0.8 seconds for it to reach its maximum location on the left. The first thing we've been asked to find is the period. One way to help us visualize what's going on here is to go ahead and look at a graph, okay, a graph of just any old sine or cosine, and just to see if we can understand why it is that this time they've given us of 0.8 seconds is 1/4 of a cycle. And what we want to notice is that a full cycle is, say from a peak to a peak, or from an equilibrium point here through that equilibrium and then back to this. Okay, and so we want to be able to see what a full cycle is, what a full wave is, and then to see that this is only 1/4 of the cycle. Because to get back to this equilibrium point, I have to go from here 1, 2, 3, 4. Okay, through 4 of those main points that we talked about the other day. All right, so the period now is 3.2 seconds, and we'll be able to use that in our other steps. So the second question asks us to find the spring constant, and we'll use that new formula that was just derived a few minutes ago here to determine that. The algebra is a little bit messy. You got to make sure that you square both sides of the equation and then rearrange things a little bit. I chose to do my algebra first and then plug things in, but you of course could first plug in your values and then just solve for k. Either way would work. But we find here that our k is 1.93 newtons per meter. All right, the next question asks us to find an equation for the position. Well, here, we have a few choices like we've talked about in class. It could be a cosine graph, a sine graph, or the negative versions of either one of those. So we need to think about this motion, and I would, kind of sketch my graph in terms of understanding this, and that's going to help me answer the question. So let me show you the graph that I would sketch, and then I'll talk through the solution. The object starts from equilibrium, and it moves in the negative direction. All right, so I started here in the middle, and then I moved down. That's the start to the graph. And from that I can see then that it's going to be a negative sine graph. And so that's why in the very end, the basic look of my formula is a negative sign. And then what I need to do is to determine the other parts of the equation, the amplitude and the value of omega. The amplitude is pretty much given to me. I'm going to put it in standard units though. The maximum displacement is 40 centimeters to the left of equilibrium. So that's where the 0.4 comes from. And then to find omega, I would use that period that I found earlier and calculate omega in that way. So our final equation that represents this motion, x is equal to negative 0.4 meters times the sine of 1.96 t. All right, and then the final question is asking us for the initial speed v sub o. And the key thing here to recognize is that v sub o occurs when the object is at equilibrium. Therefore, that v sub o that I'm asked to find is actually the maximum speed. And that's really going to be make this a whole lot easier to find, because the maximum speed can be found by taking a times omega, or the amplitude times the angular frequency. And so we can just reuse a few values from earlier in the problem and see that our initial speed, our maximum speed, is 0.78 meters per second.